In this section, we will summarize the results that we have derived so far. So we have so far we have considered the scalar form of recursive least squares algorithm, and in this we have three equations: weight update equation, gain update equation, and inverse covariance update equation. And all three of them are in the recursive form, as you can see. So the weight update equation is here, which is old weight plus the gain multiplied by the error. And then we have gain update equation, which is as listed here. And then we have inverse covariance update equation, which is shown as here. Now note that in the beginning, just for the simplicity, I had omitted the lambda forgetting factor. So once we get that lambda factor back into this derivation, there are some minor changes that are required to be done. So weight equation remains the same, just like previously. The gain update equation goes a minor change. Instead of this 1, we have lambda here. And also the inverse covariance update equation undergoes a change wherein this whole expression gets modified. So firstly, it gets multiplied by this 1 by lambda, forgetting factor, and this one gets replaced by lambda. That's the only difference. Only for the simplicity purpose, I had omitted this lambda initially, but I'll give you a hint. You can work it out for yourself. So the hint here is that if you remember, when we were driving the weight equation, optimal weight equation for the recursively square filter with the lambda included, like here. So we had come across this expression. So let's say that this numerator is called Sn and the denominator is called Rn. And let's just convert this Sn and Rn into recursive form. So I've taken Rn first here, which is the denominator part, this part, and I've written it down here. And then what I've done is I've multiplied both sides with lambda. So once I multiply this both sides with lambda, as you can see, this becomes n plus 1 minus k, which is what is written here, n plus 1 minus k. Rest everything remains the same. And now this whole expression is going till nth term. What we want is n plus 1th term. So here I'm adding n plus 1th term. So once I add n plus 1th term, this n goes to n plus 1. And in fact, this entire expression then is nothing but Rn plus 1. So with this clever manipulation, what we finally get is this Rn, the denominator, comes into recursive form, which is old Rn, new Rn, and lambda, the forgetting factor that we had defined, and new data. So that is as far as denominator is concerned. And as far as numerator is concerned, I have taken this Sn, listed it here, and again did the same thing. I multiplied both these sides with lambda, and what it does is that it adds 1 to this, so it becomes n plus 1, and to both sides I add the n plus 1th term, which is this one. When I do this n moves from n to n plus 1, which is nothing but the classic definition of Sn plus 1. So eventually what Sn plus 1 is lambda multiplied by the old Sn and this expression, which is cross correlation between the desired signal and the input signal at time n plus 1. This is the n plus 1th term. And once you have got this entire expression in this format, you will just follow the same procedures as we did earlier, and you will get these equations, these set of equations. So that's the only difference. And I also want to mention that so far we have considered this problem from scalar perspective. If we have matrix, and eventually we will have matrix form of it, because we will have a multi-tap filter, and because of multi-tap filter, it will be the weights will be vector, and also the input will be a vector. So then the filter output is defined by taking a transpose of the weight vector and taking a dot product with the input vector, and the error will continue to remain the same. That is the desired signal minus the filter output, and output is defined here. So this yn gets substituted by this expression. So that's the only difference as far as matrix form of the equation is concerned. The weight update equation remains the same. This is vector now, and so is this. And minor changes. The x square term that we get in xn plus 1 square term that we get in scalar form is now converted into this expression. If you see, this x square term is rewritten like this, and also if you see this part, So here again, a couple of square terms are there. And in matrix form, this will be, so P square K will become this, and xn plus 1 square will become xn plus 1 transpose. Similarly, the same modification is done in the denominator part. So this is the summary of recursive least square algorithm. And in the next section, we will implement Python code to demonstrate the functioning of this particular filter. In this section, we will implement the scalar RLS using Python code. The equations of the filter are written as shown in the screen. So I have imported a couple of libraries, NumPy and Matplotlib. And so I want my signal samples to be 500. And the lambda, the forgetting factor, is 0.5. Remember, it has to be less than 1 and greater than 0. And the standard deviation of the noise that I'm going to mix with my signal is 0.1. So what I'm generating is a clean 2-volt signal. So here I have generated an array of 500 ones. When they're multiplied by 2, it generates a 2-volt signal. And then I'm taking this clean signal, and the intent is to mix it with noise. So I have to generate noise. This is a Gaussian noise at 0 mean and standard deviation of 0.1 as shown here, and 500 samples to mix with the 500 samples of the signal. And here I'm mixing the clean signal with the noise to generate the noisy signal. Now I'm going to initialize the RLS variables. So remember, it's a scalar filter. There's only one weight. It's a first order filter, not a very powerful one. It's a very, very elementary way to show that RLS algorithm works. So my single weight is initialized to 0.1. It's a random choice. I can choose any number that I want. Then I have to also initialize any inverse covariance factor. So I've taken a very large number, which helps in stability of the RLS. And then I'm initializing two arrays, filter signal to store the output of the filter. And also I want to store the gains at each step. So this array is going to save that. And then I'm going to run the complete RLS algorithm. So essentially in this loop, I'm going through all the samples of the noisy signal. So xn is my noisy sample. This is the input to the filter. And then I'm also giving my filter or this algorithm a clean copy of the signal, which is the clean signal, dn. And then the first step is to compute the gain. And as you can see, the gain equation is given here, this one. So we are going to implement this here, which is exactly the same as given in the formula. And then I'm going to also, once I've calculated the gain, I'm going to save it in the array that I initialized here so that I can plot it later. And then I'm going to compute the error. And as mentioned earlier, error is nothing but the desired signal minus the filter output, and the filter output is weight multiplied by the noisy filter input. So then I'm going to update my weight. So this was my initial weight, and then I'm going to multiply gain with the error. Remember, gain was calculated here. So essentially this is what I'm implementing. My old weight plus gain multiplied by error. And so once that weight has been calculated, I'm going to calculate the output of the filter using this new weight, and I'm going to save the output of this filter. Hopefully it should be a clean one if the filter is working correctly. And then I'm going to also update my inverse covariance, Pn. Remember that inverse covariance is used in calculation of gain. So I need to update this recursively. And this is the formula 1 divided by lambda multiplied by this expression, which is exactly the same as what's shown here, the third equation here. So that's codified here in the algorithm. And then this entire loop runs till the 500 samples are exhausted. And once that is done, then I'm going to plot my clean signal, my noisy signal, my filtered signal, the gains of the filter, etc. So let me just run this code. So here we are. So the first plot is a clean versus noisy signal. And this blue line is a DC signal, as I said, that I'm generating a 2-volt signal, which is a clean signal. This blue line is depicting that. And then I'm generating a Gaussian noise, which is depicted by this red color. And that is the noisy signal oscillating at 2-volt mean. Now this red signal is the input to the filter. So the next plot is the input to the filter, which is this noisy signal, and the filter output. So the filter input is this red signal that you see, the red plot that you see, and the green is the output of the filter. And as you can clearly see that the noise has started to reduce. The amplitude of green is not swinging as wildly as the amplitude of this red signal, signifying that the noise is getting reduced. Ideally speaking, it should track this blue line, which is a clean signal, and the last plot is that of the gain, which is calculated at each step. So the gain starts off with a very high value, and then slowly it converges and start tracking the noise, so that the optimal weight is calculated and the noise is filtered out. So now we will see the effect of changing the lambda. So you remember, the lower the lambda, the lesser the memory in the system. So if I just change it to 0.1 and rerun the code, so now you can see here my green signal has got very less fluctuation, and in fact it is almost overlapping with the blue line, which is a clean signal, signifying that it is started to track the underlying clean DC signal in spite of the noise at the input of the filter, which means this RLS algorithm is working. Now the other extreme of it is that if I allow too much of memory in the system, which means if I have a large lambda, then the filter is remembering a lot of past values of the errors, and it's a single tap filter, so this will not be performing that very well. So as you can see that the green signal is almost overlapping with the red signal, indicating that the noise has not been very effectively filtered out from the system, and it is unable to track the blue line, which is a clean signal. So that is the impact of changing the lambda. We can choose any other factor. Since it's a very simple filter, just having one tap, so it does not, it cannot have a very deep memory. Had it been a multi-tap filter with 16 or 32 or 64 taps, then even a large value of lambda would have worked here. So you see at lambda 0.5, it is performing better than lambda 0.9, and at a very low value of lambda 0.1, it rejects almost all the noise and starts to track the clean signal. So that's how this RLS algorithm works. Hope you have been able to understand the theory and the practical implementation of the recursive least squares filter.